So I apologize for this really crudely drawn drawing of how an infrared spectrometer works. I don't have one to rip apart to show you. But there's a lot of components that go into an infrared spectrometer. Let's talk about practically what happens when you do an IR and why we have to take the Fourier transform to make this work. So, heart and soul of any IR is its IR source. Basically, it's a lamp, it's a bulb that generates infrared light of a fairly narrow range. What we're going to do is we're going to pass that light into what's called an interferometer. So, old ones, I don't know if they still do this, is basically a glass cube cut across, basically cutting the cube in half. And what happens is that you pinch the frequencies between two edges, and only certain frequencies are favored at the given angle. Now, the interferometer is actually moving back and forth during this measurement, and so it's going to select different frequencies at a given time. Now, we know the position of the interferometer is a function of time. So this is where our time dependence on the spectrum comes from. We're sweeping back and forth a whole bunch of frequencies at a given rate. This light interferometer will select out the certain given wavelength and will pass it through a splitter. This splitter diffracts the beam into two parts. One is the reference beam, which will go to detector 1. The second is through the sample, which will pass through and hit detector 2. Now, our detectors, there's two grades of these. There's the cheap silicon ones that work basically just fine for room temperature. There's also the really super nice germanium ones that require liquid nitrogen cooling. If you're working with that, power to you. Probably not doing that with the general organic chemistry course though. So practically what we do is we measure D2 over D1 versus time. And this is what the detectors are actually measuring, is this ratio of their signal intensities. This D1 over D2 here is your transmission. So we get transmission versus time. So if you were to look at an interferometer spectrum, you would probably get some type of noise if you were looking at the raw signal. I mean, it would make sense and it would be a pattern, but it wouldn't be a pattern that you could readily translate into something meaningful. So what we're going to do is take what's called a Fourier transform. And what a Fourier transform does is it converts our time into frequency. And we know this conversion because we know how fast we're rocking the interferometer back and forth. This conversion here takes us from transmission versus time to transmission versus frequency. And we're going to work with units of wave numbers, which is inverse centimeters. This is what you see when you take an infrared spectrum, a Fourier Transform infrared spectrum, or FTIR. So this is the most commonly reported infrared spectrum. There are others. There are other ways of doing this technique, but the FTIR is basically the most practical way of doing it. So this is where we're going to see transmission, and we're going to see different wavelengths and different shapes corresponding to the different functional groups within the molecule itself. Now again, we kind of need this reference spectrum so we know actually how much is being absorbed relative to the signal, because I've drawn this out kind of nice and ideally, but it doesn't necessarily mean that the signal intensity put out by the bulb is the same for all wavelengths. So this is practically what's going on in your FTIR. We're going to work primarily in transmission mode, but I'll probably put up a special video about the different techniques as well, just so you're aware of what else is out there.